Okay guys, for the first part of this, we're just going to do a little investigation. So just as a reminder for you, x values, so a function is considered increasing as you move left to right, or as the x values are increasing, the y values will be decreasing. So we're taking a look at the red function here. I know that yours is in black and white, but we're taking a look at this function right here. The quadratic is the function of the derivative. And we're going to examine what's going on with the original function f at x and how that relates to the function f prime at x. So first I just want you guys to decide on where f at x is increasing and decreasing, and then say what you notice about f prime at x when f at x is increasing and f prime at x when f at x is decreasing. So essentially the little test that you can do is if you're moving from left to right and your pen is moving up on the graph, it's increasing. If you're moving from left to right and your pen is going down on the graph, it's decreasing because the y values are decreasing. Okay, so see if you can decide over which intervals f at x is increasing and decreasing. I'll give you a couple minutes to do that. All right, so who can tell us over which intervals f at x is increasing? Kristen? So you're saying 0 to -3? Okay, so we can say negative infinity to -3. Are there any other increasing intervals? Here to here? Or just to here? I think it's increasing past 3. This function goes on forever in both directions. So 1 to what? Yes, positive infinity. So we'll say in union with 1 to infinity. If you'd like to use inequality notation, you can say where x is less than 3 and greater than 1. Okay, so basically we're saying from negative infinity all the way to 3, we're increasing, and then from 1 to positive infinity, those are the increasing sections of f at x. So if f at x is increasing along these intervals, where is f at x decreasing? Michael? In between, right? So -3 to 1. Or you can say it like this in inequality notation. Okay, so that would be the intervals kind of in between all along here. Okay, did you guys notice anything about the connection between f at x and f prime at x when f at x is increasing? Essay?
When f at x is increasing, f prime at x is above the x-axis.
Right, so all the way up to this point right here, when we're increasing, you'll notice that f at x is in the positive section of the graph. So the y's there are positive. So f at x is positive when, or f prime at x is positive when f at x is increasing. And when we say positive, we mean it has positive y values. In other words, it's above the x-axis. Okay, so we can see that in this section over here, and we can also see that in this section over here when we're increasing. F prime at x is in the positive section. V? Positive. Plus. Positive. Positive.
Or negative.
I will just write positive for you. Okay, so if f prime at x is positive when f at x is increasing, what do we know about f prime at x when f at x is decreasing? Michael?
When f at x is decreasing, f prime at x is below the x-axis.
Okay, so f prime at x is negative when f at x is decreasing. So in other words, we're saying that the y values are negative. The y values of the derivative function are negative, meaning they're below the x-axis. Okay, so we can see that for this section here, this blue section that I've highlighted for f at x. You can see this whole section of f prime at x is below the x-axis in between that area where we're decreasing. Okay, so in conclusion, we can say when f prime at x is greater than 0 or positive, f at x is what? Increasing on that interval. Perfect. And when f prime at x is less than 0, we can say that f at x is decreasing along that interval. Okay, so increasing and decreasing is something that we're going to be exploring this chapter. We're also going to be exploring things called critical numbers. So critical numbers are going to be some value that is in the domain of your function f at x, where your first derivative at that value, so f prime at your a value, is either equal to 0 or does not exist. Okay, so we're going to look at a couple examples here. So critical numbers can give us information about f at x in the sense that where the derivative is 0, so you'll see in all of these examples here, your first derivative is equal to 0 at these points. There's a couple different things that we can see from f at x here. So here, when your derivative is 0, this is actually a local max right here. So we'll get the first derivative being equal to 0 here. Okay, and we can also see from the first derivative that we change from a positive section to a negative section of the graph. So if we're changing from a positive section to a negative section in the first derivative graph, we're actually changing from an increasing part of the function to a decreasing part. If I change from increasing to decreasing, that's causing a local max, right? If I'm increasing and then I change to decreasing. So those are a couple of things that we can look at from the first derivative. Okay, so we will see a change. F at x changes from positive to negative here. Okay, so here it's in the positive section and then it goes into the negative section. This tells us that there's a local max at f at x, and f at x is changing from increasing to decreasing. Yep.
So for the local min, does the same thing happen where at the point where it's at the minimum, the derivative is equal to 0 there?
Yes, so basically what we're saying is that the slope of the tangent at this local max part is equal to 0. Okay, so that's for both local max and local min. We're going to see that, of course, at a turning point, the slope of the tangent equals 0. So same thing here, we have a local min at this point. So slope of the tangent is equal to 0. That's what causes the 0 to occur for the derivative function. Okay, so this one we can see actually changes from negative to positive, and that's because the original function is changing from decreasing to increasing, and that's what causes the local min to happen. If I change from decreasing to increasing, I must have a valley happening there, right, where I have a local minimum. So you'll notice that f at x, or f prime at x, changes from negative to positive. And that's because f at x changes from decreasing to increasing. Okay, and if we change from decreasing to increasing, that means we have a local min. Okay, so these are scenarios where f prime at a equals 0, right? So these three scenarios. Temi?
No, never mind. I answered.
Okay. And then this guy here, we actually do have a tangent slope that is equal to 0. But you're going to notice that our first derivative actually remains positive here. So it's positive, and then it actually stays positive here. So although we do have a 0 of our first derivative, we actually don't have a local max or a local min, because you'll notice that the original function is increasing and then continues increasing here. So in order to produce a local max or a local min, the function must change from increasing to decreasing or decreasing to increasing. If it's always increasing or always decreasing, even if the slope of the tangent is 0, somewhere in between there, we have neither a local max nor a local min. Okay, so you'll notice that f at x does not change in between there. Okay, it changes in other areas, but in this specific area that we're looking at 0. Okay, and we'll notice that f at x is increasing at this particular area. Okay, it does change from increasing to decreasing in other areas, but we're just looking at the highlighted areas in the boxes here. Okay, the other scenario that we could potentially have is an area where the derivative doesn't exist. Okay, that would be something like a cusp. So in this scenario right here, we have a point right at this cusp that is clearly a minimum point for this graph. But the tangent actually is not equal to 0 here. The tangent actually doesn't exist on something like a cusp, because we could balance this tangent in a variety of different ways because there's no curve, right? So if there's no curve there, then the derivative here actually does not exist. And you'll see that this actually is producing an area that's undefined in the derivative as well. So it's actually producing an asymptote here. So f prime at x in this scenario for the highlighted area does not exist. Or maybe I should say f prime at a. Okay, because it exists in other areas. And you'll notice that at f at a or f at 0, there is a cusp. So actually I'll say f at x changes from decreasing to increasing. Okay, so we do have a minimum in this scenario, but the first derivative does not exist. So we always need to kind of look at what's happening where the first derivative is equal to 0, but also where it does not exist, because that could also produce some kind of maximum or minimum. Okay, so f prime at a does not exist. That would be an example.
Can you go down top of this?
Yep.
Is it always going to be an
Pardon?
Is it always going to be an asymptote?
If the derivative does not exist at a point, then that usually will produce some kind of asymptote. But yeah, you'll have to, it's different for every function for what's going to happen.
So if that cusp happened at like x is equals to -8, that's where
That would be where the asymptote is, yeah. Okay, so those are just some scenarios that you could see when your first derivative does not exist or your first derivative is equal to 0. So our conclusion is that these things called critical points that we just talked about, or critical numbers, they are called critical numbers because they can produce things that we call local extrema. So local extrema would be like local max, local min. Okay, and the sign of the derivative must change around that area. So here we'll notice again that the derivative, the sign of the first derivative is changing from positive to negative. Here we're changing, sorry, that was supposed to be a positive there. Here we're changing from negative to positive. And again, here we had neither because it was positive and positive. So you can kind of look at how your first derivative sign is changing. Also, this one, we have a negative section and a positive section. So f prime at x actually does change from negative to positive here. Yep.
What do you mean by a local max or a local min?
So this is what local max and local min. So areas where we have like a mountaintop or areas that we have like a valley. So generally in that area, that's the highest point in that particular area of the function, or it's the lowest point in the particular area of that function.
I was just confused because like there was another min.
Yeah, so there are also, like for instance, this is a local max and this is a local min.
Okay, so they're all okay.
Yeah. Tammy?
For the local min one, the derivative, is it going, it should be like the positive, right? Negative to positive.
Yes, negative to positive.
Wait, what? Oh. So where do you start from? Because the first one you started like at the top of the function and then the second.
So we're just examining like a couple particular areas of this function. Like I said, these functions have other local maxes and local mins in them. Like this one, for instance, this has a local max right here, a local min right here, and another local min over here. So I'm just looking at specific areas of the function to show you a couple scenarios here. Okay? Okay, so local extrema can occur if the sign of the derivative changes from positive to negative or negative to positive. If your sign of the derivative does not change, you don't have any local extrema, okay? So we don't have a local max and we don't have a local min. That would be like this scenario. That point right there, it has a tangent equal to 0, but it's increasing and then it continues to increase. So the sign of the derivative is always positive surrounding that area. Critical numbers, they have to be in the domain of the function. So firstly, like if I say that something's going to be a critical number, it needs to be defined for f at x. And it's going to happen where f prime at x has a value that's equal to 0, or where the derivative does not exist along the function. If I take that a value, wherever that is along my function, where the derivative is equal to 0 or does not exist, and I plug it back into my function, I'll get an xy coordinate. That's called a critical point. So critical numbers are your x values. Critical points are like the xy coordinate. Okay? Critical points, we can't automatically just say because the derivative is 0 or does not exist that they are local extrema. We have to do a test to see what's happening around those critical points, and that's called the first derivative test. Okay, the first derivative test will give us more information about whether we have a local max, a local min, or neither. Oh, sorry, first derivative test. Okay, if this isn't quite making sense to you right now, that's totally okay. Once we apply it, it will make a little bit more sense. Okay, the big thing that you need to take away from this is that critical numbers occur where the derivative is equal to 0 or does not exist, and then we have to do further testing to see if the sign of the derivative is changing around it or staying the same.
Just be curious.
Yeah.
So you say if a is a critical number, that means if a is at 0, if the x value at a is 0, right?
So if the x value, so this we're saying slope of the tangent. So slope of the tangent at that particular x value would be 0. Okay, let's apply this and kind of see what's going on here. Okay, so determine all local extrema for the function below using critical numbers and the first derivative test. State when the function is increasing or decreasing. Okay, so firstly, I need to know where the derivative is equal to 0 or where the derivative does not exist. So we need to find the derivative to start. Okay, this derivative function is a quadratic. Is there anywhere where a quadratic is going to be undefined? Does it have vertical asymptotes or undefined points or anything like that? No. So this function is defined everywhere. Now I just need to know if it's equal to 0 somewhere. Okay. Okay, so we're going to factor to solve here. Okay, basically polynomial functions, guys, are going to be defined everywhere. Like their derivatives and them, they're going to be defined everywhere. Areas where a function is like undefined are going to be produced by like other types of functions, like rational functions and things like that. So if you're doing the derivative of a polynomial, like it's going to be defined everywhere. So you're just interested in where that's equal to 0. So for this one, it's going to be where x equals 4 and where x equals -1. Okay, so in advanced functions, when we were analyzing things like polynomial inequalities or rational inequalities, we did something called a sign chart. So we're going to do the same thing, and we're going to analyze what's happening with the derivative and also make a conclusion about what's happening with f at x. So we're going to kind of create this like number line type thing on the top like we did in advanced functions. Okay, I usually do like a negative infinity marker and a positive infinity marker, and then you need enough lines in between for the number of x values that you have. So lowest to highest, we're thinking of this again as a number line, so going from negative infinity all the way to positive infinity, arrange your x values in order. And then we're going to decide what's happening with f at x, f prime at x with our test values, and use that to determine what's happening with f at x. Okay, so just like we did in advanced functions, we're going to choose some test values that fall in between these intervals that we can plug into our first derivative function and record whether we get positives or negatives. So something between negative infinity and -1, maybe we can choose -3. Something between -1 and 4, 0, yes, very good choice. 0 is probably easiest if you can put that in there. And then 4 to infinity. Maybe like 6 or something like that. Okay, we're going to test these in the first derivative function. You can test it in the factored form or in the expanded form, up to you, whatever you find easier. And we're just going to record whether we get positive or negative for the first derivative. So plugging in -3 in here and seeing whether you get positive or negative. Okay, so for the first one, we get 6 times a negative times a negative. That will give us a positive. Okay, and that means that the function f at x is increasing. So it's moving up toward the right. Okay, when the first derivative is positive, remember we made this conclusion above, when the first derivative is positive, that means f at x is increasing. Okay, now sub in 0, we're going to get a positive times a negative times a positive. That will give us a negative, telling us that f at x is decreasing, meaning it's going down toward the right. Okay, and then if we plug in 6, we'll get a positive times a positive times a positive. So that will give us positive. That tells us that f at x is increasing. So it's going up toward the right. Okay, so here, if I change from increasing to decreasing, what does that tell me we have in that area? This must be a local max, right? Now, if I change from decreasing to increasing, in this area, we must have some kind of little valley happening, right? So we have a local min here. Okay, so these x's here, these are called our critical numbers, right? These are where our first derivative is equal to 0. Now, if I want to identify the local extrema, I ideally would like an xy coordinate for this. So now that we've identified these as local maxes and local mins, the final local extrema values, local maximum point and local minimum point, can be found when we evaluate the function for f at -1 and f at 4. So we're just going to plug that in quickly here to find our points. So in for the original function, we're just finding the xy coordinate. Okay, help me out with calculating those, please. Grab your calculators out. Did you guys get 3 for the first one?
Yep.
Okay, anyone have the last one for us? Did everyone else get negative 122 here?
Yeah.
Okay, so these are called critical points, right? So the critical numbers are the x value, and then the critical points are going to be at negative 1, 3, and 4, negative 122. Okay, and then we can classify these, so we can classify these critical points as the local extrema, or sometimes called local extreme values. And then we would classify them as local mins or local maxes, or neither, based on whether the function is, whether the derivative is changing from positive to negative, or negative to positive, or not changing. So negative to negative, or positive to positive. So our local extrema, we have a local max at the point negative 1, 3, and we have a local min at the point 4, negative 122. Okay, so this little test that we did up here, seeing what's happening with the first derivative, that's called the first derivative test. And we use a sign chart in order to test that. So if you want to label that, you can. Okay, obviously this is also part of that first derivative test because we need to see where the first derivative test is equal to 0 first in order to create this sign chart. Okay, any questions on this so far? Essay.
I still understand why f(x) being all in the max f prime x makes f(x).
So if f prime at x is positive, we're saying the slopes of the tangents are positive there. So the function must be increasing in that area, right? It must be going up toward the right. And then same thing, f prime at x is negative. We're saying the slopes of the tangents are negative there, so the function must be decreasing. Does that answer your question? Okay, can I scroll? Okay. All right, so essay, this might also help further answer your question. So just so that you guys can see what's going on graphically here, we can see that in this area right here, f at x is increasing, and similarly, in that same area, f prime at x is positive, right? Then we have like our little turning point here. That's our local max. Okay, and this is where our derivative is changing from positive to negative. Okay, or in other words, it's where our original function is changing from increasing to decreasing. Okay, that's what this sign chart is telling us, this area of the sign chart. Okay, and then we can also look at where the function starts decreasing. So here, f at x starts decreasing all the way to this point here. And we can see in that area that our derivative function is negative. So this whole area right here, the derivative function is negative. Then here we have another critical point. This is a local min. And we change back to increasing. Okay, so the original function changes from increasing to decreasing, that's local max, decreasing to increasing, that's a local min, and then we're seeing that the derivative function is changing from negative in this section to positive up here. Okay? So that's kind of what we're analyzing when we analyze that chart. Okay, so we're going to do kind of the opposite now. So we're going to look at the graph of the derivative and sketch some possible functions for f at x. So we've done some of this stuff before, like a little bit in our first unit, but we're just going to kind of see if we can expand our knowledge now that we know about positive and negative for the first derivative and stuff like that. So our derivative is basically equal to 2 everywhere. So that means that the slope of the tangent for f at x must be constant, right? If I have a constant slope for my function f at x, that must mean I have a line, right? If the slope is the same everywhere for the original function, then it must be just a line that has like a consistent slope, right? So, and I can actually figure out what the slope of that line is. What's the slope of the line if the derivative is always equal to 2? 2. So f at x must be a line. Oh, sorry, negative 2. Must be a line with a slope of negative 2. Also, what do we know about the original function based on the fact that f prime at x is negative everywhere?
It's decreasing.
Yes, so it must be decreasing. Okay, so we need to draw some line that's decreasing everywhere. Obviously, if it has a negative slope, it is decreasing. And we don't really know exactly where that line is. So as long as you have a slope of negative 2 and your line is decreasing everywhere, you're fine. So we really don't know where the y-intercept is of that line. So we could put the y-intercept, let's say, at 1, and then we could just go down 2, right 1, down 2, right 1, and just draw this line, okay? This line, again, as long as it has a slope of negative 2, you're good to go. We don't really know where that y-intercept is, but this could be a potential equation or a potential graph of f at x. Okay, so I can have this line kind of slid anywhere along this function. Okay, let's look at the second one here. For our second one, we have a line. Remember how we talked about in our first unit how the derivative, like if I'm doing derivatives of polynomial functions, the degree goes down every time I take the derivative? Okay, so if we have a linear function as the derivative function, what must be f at x?
Oh, a quadratic function.
Okay, so here we could say f at x is a quadratic. Okay, what else do we know about f at x based on the graph of f prime at x? Essay? So it has one turning point, right? So one area where the derivative is 0. So it has a turning point. So if f prime at x is degree 1, f at x must be degree 2, right? Because every time we take the derivative, the degree drops again. Okay, it has a turning point or some kind of local extrema value when x equals 2. Okay, what else does the graph of the derivative tell us about f at x? What's up? Pardon? Okay, so we're changing from positive here to negative here, so this must be a local max. And what else does the positive and negative parts of the derivative tell us about f at x? Where is f at x increasing and where is it decreasing?
It's increasing before to and it's decreasing.
Okay, so it's increasing from negative infinity all the way to 2 because that's where the derivative is positive. And then it's decreasing from 2 to infinity because that's where the derivative is negative. Okay, so possible graph of f at x, we need to have a vertex. This is a quadratic facing down because it's going from increasing to decreasing. I don't know where this vertex is as far as the y value. I just know that the x value has to be 2. So we could have it maybe up here. It could be anywhere really along x equals 2, and then it's opening down. So it's increasing all the way up to the vertex point, and then it starts decreasing. Okay, so this is just a possible graph of f at x. You guys might have something different than what I have, right? Okay, technically your x-intercept should be equidistant from the vertex, right? Meaning like if I have an x-intercept at 0, then the other one must be at 4 in order to have a vertex at 2. So you could also like just make sure that your drawing kind of has like equal distances from that vertex for x-intercepts. Can I scroll? All right. F prime at x. So if f prime at x is a quadratic, what could we say about f at x? Okay, so it's probably degree 3. Or a cubic. What else do we know? What does this tell us?
We have a local max at 2.
Okay, so we're changing from decreasing to increasing.
Local min at 2.
Oh, sorry, it's positive and positive here. So what does that tell us? Okay, so the function keeps increasing everywhere, but we do know that f prime at 2 does equal 0. So the slope of the tangent must be equal to 0. Yeah. So the slope of the tangent must be equal to 0 for f at x at that point. Anis? I mean, for this one, I'm pretty confident that this is a quadratic, but once we get into like degrees that are higher, like this could be, like it seems quite round, so I think it's a quadratic, but it could be like a simple degree 4 polynomial, so like, yeah.
I'm just curious.
Mm-hmm.
So don't degree 3 functions have to start in a positive quadrant and end in a negative, or like start in a negative and end in positive?
Sorry.
Aren't they shaped like a weird S shape?
Yep, so this will be S-shaped likely, yep.
Okay, so then how do we go from negative to positive to positive if it's like S shaped?
Okay, so f at x is increasing everywhere. I'll answer your question in a second. F at x is increasing everywhere except for obviously when x is equal to 2. So I need to draw a function that's increasing everywhere, but it has a horizontal tangent when x equals 2, but then continues increasing. So this cubic has some point along here. Again, I don't know where that point is, but it has some point along here where I'm going to have a horizontal tangent, right? So somewhere along here, but it needs to be increasing everywhere. So it's probably like a degree 3 cubic that kind of goes like this. Right, and then in between there we have that area where the slope of the tangent is equal to 0. Right, so something like this.
The horizontal bit still be on like the x-axis?
Yeah, that again, that graph could be shifted up and down anywhere along there. This is just a potential graph of f at x. Okay, and then for the next one, I think we could again say that f at x is likely a degree 3. Pretty sure that's a quadratic, right? Or we at least know that it's an odd degree, right? What do these values tell us right here? 1 and 5.
Local min and max.
Okay, so we have, which one's local min, which one's local max?
5 is the minimum and 1 is the max.
Okay, so if we're changing from positive to negative, we're changing from increasing to decreasing. So there must be a local max when x equals 1. And then again, if we're changing from decreasing to increasing, when the derivative changes from negative to positive, there must be a local min when x equals 5. Okay, and then we can also say f at x is increasing from negative infinity to 1, and also 5 to infinity. And f at x is decreasing in between those values. So from 1 to 5. It just means in union with, so it means like and. Okay, so why don't you guys see if you can graph a potential graph of f at x. See if you can figure it out. Yep.
Have to go for 3. That's where it's like the most.
What do you mean?
And then max after the targets. Like,
Okay.
I put my function like going through point 3.
It will go through 3 somewhere. It doesn't have to be like an intercept. Yeah. Okay, so we need some local max somewhere along here. Again, I don't know where that is, but let's just say if our function is increasing, maybe the local max is there, and then it starts decreasing. Okay, and I have to have a local min somewhere around here, so could be something like this, or maybe a little bit, make that a little bit better. Okay, maybe something like this. And then maybe it starts increasing again here. Okay, again, I don't know where those turning points are. I don't know how high or how low that goes. So it could be any kind of shifted version of this graph. I don't know what that was. Okay, so you want to make sure that your f at x function is lined up somewhere with these, like the turning points here are lined up with the zeros on your derivative function. At the very least, and then you need to have obviously the correct increasing section, the correct decreasing section, and then increasing again. Any questions on these ones? Okay, so a couple more. So we have some continuous functions. This tells us that f prime at x is less than 0, or is greater than 0, or in other words, positive, when x is less than 0. So what does this tell me about f at x? F at x is what? So the first derivative is positive when x is less than 0. So does that mean f at x is increasing or decreasing?
Increasing.
Okay, so f at x is increasing from negative infinity to 0, or when x is less than 0. Okay, and then what does this second part tell us? F at x is less than 0. Sorry, this part right here. F prime at x is less than 0 when x is greater than 0. So f at x must be increasing or decreasing here? Decreasing? From 0 to infinity, or if you're using inequality notation, when x is greater than 0. Okay, and I also have a point on my function. It's 0, 4, so let's plot it. So this must be a quadratic, right? If I'm just changing from increasing to decreasing, this must just be like a curve that where the vertex is up here, right? So here's my increasing section. That wasn't great. Okay, and then here's our decreasing section. Something like this. Okay, whether that is like this or like this, I don't really know, right? So as long as you have a parabola that has a vertex up at 0, 4, and it's increasing on the left side and decreasing on the right side, you're good to go. Okay, can I scroll from this? Essay? F at x is greater than 0? So this means the first derivative is positive.
When x is less than 0.
Yeah, on this side over here.
So it's positive?
That's the derivative. The derivative is positive. We're graphing f at x. Okay, so the derivative, again, whether that's positive or negative, tells us information whether f at x is increasing or decreasing. So that's why we have f at x increasing here and then decreasing here. Can I scroll from this one?
Yeah, let's be careless.
Yep.
And for this one, the first derivative would be a line, right?
The first derivative would be a line. Yep.
Wait, so if f at x is positive, then means this side's going to be negative. And then since that one is negative, this side.
So if f prime at x is positive, then this side must be increasing as we move from left to right.
And the other one's negative,
So it's decreasing, yeah. Okay, let's try another one. All right, I have a point. It's f at 0 equals 0. Let's plot it. I also know that between -1 and 2, the first derivative is negative. So what does that tell me about f at x? Okay, f at x is decreasing. Okay, so if you want, you can do like little kind of lines here to separate and then just erase them after. But I know in this section that f at x has to be decreasing. And then I know in the opposite sections, so when x is less than 1 or x is greater than 2, that the first derivative is positive. So what does that tell me about f at x? Okay. So on those values, at -1 and 2, at -1, my function actually changes from increasing to decreasing. So what do we have at -1? Yeah. Okay, the area is changing from increasing to decreasing, so there must be a local max there. And when x equals 2, what's going on? Well, this section is the decreasing section, and then I'm increasing over here. So what must I have when x equals 2? Some kind of local min, right? So here's what we need to do. We need to make sure that our graph has some local min and local max points. It needs to go through this area right here, and it needs to be increasing here, and decreasing somewhere in here. Okay, so this looks like it's shaping out to be a cubic, right? So I don't know where the local max is. I'm just going to plot it somewhere, right? Like maybe it's here. And the section of my graph is increasing. And then it starts decreasing. And then I have some local min. Again, I don't know where it is. I'm kind of trying to make this somewhat symmetrical because it's a cubic, I think, right? And then it starts increasing after that. So something like this. If it's not super symmetrical, it's not a big deal, as long as you have the right idea. So increasing, and then we have the decreasing section here, like we said, and then you plot the point at 0, 0. So your graph needs to go through that. Okay, and then if you want, you can just erase these little sections here. Any questions? Okay, those ones will probably take a little bit of practice just to kind of get used to what the information is telling you. Okay, last one, application. So the temperature of a person with a certain strain of flu can be approximated by the function T at D. T is representing the person's temperature in Celsius, and D is representing number of days. We are looking for where days is from the initial observation to day 6, basically. So this is telling us that that's the window of where we're looking at the person's temperature. During what interval will the person's temperature be increasing? Okay, how can I figure out where a function is increasing? What can help me with that? The first derivative. Okay, so let's find T prime at D. Just applying power rule here. And I'm setting the first derivative equal to 0 because we need to find where the critical number is here. So where is the point where the person's temperature is increasing and changing to decreasing, or vice versa, right? Okay, so we're just going to isolate for D here. Okay, easiest way to get rid of a fraction is just to multiply by its reciprocal. So I'm going to multiply each side by 5/9 to get D by itself. Not negative reciprocal, just reciprocal. Okay, if I multiply by negative, then I'm going to find negative D. It's not what I want. Okay, this is a critical number. So when we're at day 3, there's a possible change in the person's temperature here. Maybe they're going from increasing to decreasing or decreasing to increasing. We'll see what happens. We're going to use that first derivative test chart to see what's going on. Okay, and normally I put negative infinity and positive infinity here, but we do have a restricted interval here. It's from 0 to 6. So I'm going to put 0 and 6 here, and then we'll put 3 days here. Kaylee?
Why don't you put negative infinity?
Well, I can't really go into the negatives for days, and we're only going up to day 6. That's what this question is telling us, so it goes from 0 to 6 only. Okay, this person probably doesn't have the flu forever, hopefully, right? So we don't really want to go to infinity. Right. Okay, so choose some test values inside those intervals. So maybe we'll choose 1 and 5. And we're just going to plug them into the first derivative and just record whether we get positive or negative. Okay, so I think for the first one, we're going to get positive when we plug in 1.
Yeah.
So that tells us that the temperature is increasing over that interval. And then I think if we plug in 5 here, we get negative 25/9 plus 15/9, so that gives us a negative. So from day 3 to day 6, we're seeing that the temperature is decreasing. Okay, so the answer to our question here, during what interval will the person's temperature be increasing? We could just make a therefore sentence. Therefore, the person's temperature will be increasing from day 0 to day 3. Okay, at some point during the 3rd day, they're going to reach a maximum, right, where then the temperature starts decreasing. Any questions on this one? Okay, so key takeaways here. When the first derivative equals 0, we have a critical number. Or where it does not exist, we also have potential area where the function could change from increasing to decreasing. We analyze the first derivative to see what's going on with f at x. Is it changing from increasing to decreasing, decreasing to increasing? Is it not changing? And then we can classify our local extrema values. So local min, local max, or maybe we have neither, right? And then, yeah, so that's basically all the information from today in a nutshell. Okay?